Subject name is Computer Architecture. Title of the unit is Parallelism. Topics to be covered in this session is hardware multithreading, multi-core processor and other shared memory multiprocessor. Thread level parallelism. Instruction level parallelism exploits very fine grained independent instructions. Thread level parallelism is explicitly represented in the program by the use of multiple threads of execution that are inherently parallel. Goals: use multiple instruction streams to improve either throughput of the computers that run many programs, execution time of multi-threaded programs. Thread level parallelism potentially allows huge speedup. There is no complex superscalar architecture that scales poorly. There is no particular requirement for very complex compilers. Instead, the burden of identifying and exploiting the parallelism falls mostly on the programmer. Programming with multiple threads is much more difficult than sequential programming. Debugging parallel programming is incredibly challenging. It's pretty easy to build big, fast parallel computing. However, the main reason we have not had widely used parallel computer in the past that is too difficult and time consuming and error prone to program. Find a way to hide true data dependency stalls, catch miss stalls, and branch stalls by binding instructions that are independent of those stalling instructions. Multithreading increases the utilization of resource on a chip by allowing multiple processors to share the functional units of single processor. Multiprocessor must duplicate the state of hardware for each thread, a separate register file, program counter, instruction buffer, and stored buffer for each thread. The catch is DLPs, branch predictors, can be shared. The memory can be shared through virtual memory mechanism. Hardware must support efficient thread context switching. Fine grained multithreading switches the thread on every instruction, issuing resulting in interleaved execution of multiple threads where interleaving is round robin fashion. Processor must be able to switch threads on every clock cycle. Advantages and high throughput losses that come from both short and long stalls. Disadvantages: slow down the execution of an individual thread since a thread that is ready to execute without stalls is delayed by instruction from other threads. Coarse grained threads switches threads only on costly stalls. Advantages: thread switching does not have to be essentially free and much less likely to slow down the execution of an individual thread. Disadvantages: limited due to pipeline startup cost. In its ability to overcome throughput loss, pipeline must be flushed and refilled on thread switches. A variation of multithreading that uses the resource of multiple issues dynamically scheduled processor to exploit both program instruction level parallelism and thread level parallelism. Most superscalar processors have machine level parallelism than most program can effectively use. With register renaming and dynamic scheduling, multiple instructions from independent threads can be issued without regard to dependency among them. Need separate rename table for each thread. Need the capability to commit from multiple threads in one cycle. Intel recently desktop and laptop processor mostly use SMT. The hard part of building a processor with SMT is not designing the SMT hardware. SMT hardware relies on parallel instruction execution on out of order processor. It's very simple. If two instructions belong to different threads, then there is no dependency. The hard part of building SMT processor is designing and building the underlying out-of-order superscalar processor architecture. Testing and debugging the processor in SMT mode. Parallelism is so fine-grained that it's hard to investigate, and there can be any order of execution of instruction from different thread. This diagram represents the SMT or multi-threading architecture, which is going to use coarse multithreading, fine multithreading, and SMT multithreading. In coarse multithreading, we have 4 threads with 2 instances. In coarse multithreading, thread A is going to be completed. After the completion of thread A, it's going to complete thread C and D. This process is going to be continued till the end of thread D. In fine-grained multiprocessor, first 2 instruction slots of thread A is executed. After that, 3 slots of thread B is executed, and first 3 slots of C is executed, and 1 slots of D is executed. This cycle is going to be completed till the end of thread C. In SMT threads, 4 slots is allocated for SMT. First 2 slots is issued to thread A, and remaining 2 slots is going to use to complete the first slots of thread B. In the second step, first slot of thread B is completed. After that, it's moved to thread C. This task is going to be completed till the end of thread D. Now we will see what is processor. A processor is a logical circuit that responds to process the basic instruction that derives computer. The term processor has generally replaced the term central processing unit. The processor in personal computer or in small devices often called multiprocessor. Types of multiprocessor is single core processor, multi-core processor. Single core processor. It is a processor that has only one core, so it can only start one operation at a time. It can, however, in some situations start a new operation before the previous one is complete. Originally, all processors were single core. Multi-core processor. A multi-core is a single computing component with 2 or more independent actual central processing unit, which are the units that read and execute program instruction. Types of multi-core processor. Dual core processor, quad core processor. Dual core refers to CPU that includes 2 complete execution core per physical processor. It has combined 2 processors onto a single integrated circuit. The processors are well suited for multitasking because they are 2 complete execution cores instead of 1. Quad core processor. The quad core processor is a chip with 4 independent units called cores that read and execute central processing unit instructions such as add, move, data, and branch. Quad core and high multi-core processor configuration have become common for general purpose computing, not only for PC but for mobile devices such as smartphones and tablets. The basic need of multi-core processor is parallel computing. Time consumption is the fooling drawback of single core processor, so multi-core technology has become the mean to achieve efficiency through parallel processing. Processor memory types: shared memory and distributed memory. Shared memory, there is one common shared memory for all processors. Distributed memory, in this model, each processor has its own local memory and its content is not replicated anywhere else. Why multi-core? Better performance, economical efficiency, save the room of motherboard, parallel computing. Shared memory multiprocessor. There are three types of shared memory multiprocessor: uniform memory multiprocessor, non uniform memory multiprocessor, cache only memory. Uniform memory access. In this type multiprocessor, all processors share a unique centralized memory so that each CPU has same memory access time. Second type is non-uniform memory access. In this non-uniform multiprocessor module, the access time varies with the location of memory word. Here the shared memory is physically distributed among all the processor called local memory. So we can call this as distributed shared memory processor. Cache only memory. The comma module is a special case of non-uniform memory access module. Here all the distributed local memories are converted into cache memory. Data can migrate and can be replicated in various memories but can't be permanently or temporarily stored.